I will just get started. So, quick recap. We have been talking about parametric equations, and we had all this writing, and we came down to we had two things. We got this vector equation of a line down here, and then from that we stemmed to these parametric equations down here. And I just wanted for us to remember that these equations didn't come out of nowhere, and they weren't super hard to get either, right? They both came from just here's a line, right? If it's parallel to this vector, that's how we get this vector equation. That's how we get this vector equation. And then from this vector equation, if we set x minus x1 equal to t times a1, right? And similarly for y, that's how we got these. Not too much. It's just something you should have written down in your notes, just so they didn't come out of thin air. Then we wrote an equation in example 2. And then in example 2, we got these two parametric equations. And I just want us to notice and kind of like remember, like, the reason we're doing this is because a lot of times in physics or the real world, things are dependent upon time or velocity or initial position, in which parametric equations are really useful. So in example 2, I mean, it just said, hey, write a parametric equation for this, which on the surface seems like, okay, what do we use that for? But the idea is you learn the abstract so that you can apply it to the real world later, right? You learn how to do a parametric equation, so then later on you can make a parametric equation of a real world scenario, right? There's millions of real world scenarios in which time is a factor in something's position, right? That's so broad, right? So that's kind of the idea. And so each value of t gave us an ordered pair xy, and that coordinate xy can be considered the position of an object at various times t, right? Like I said, the world can be a graph if you make it a graph, right? So, and then I just rewrote this stuff real quick. We ended up getting these two equations, and if we plugged these values of t in, these are the x and y values we got. Right. So that was the quick recap. I'm going to go through two more examples today. Example 3, write parametric equations for y equals negative 4x plus 7. So before we were given like a point and a vector, and this time we're straight up given the line, right? And it's basically asking us to write another equation for this line, but this time we're doing it in the form of a set of parametric equations. And there's kind of a dirty little trick here. And to do it, I have a little participation sheet here. Just one question, which I probably have asked before in this class. When we're talking x and y, which one is usually the independent variable? X or y? Anyone? Oh, if it's a chat, sometimes my chat doesn't open up. Y. It is indeed actually x. And the way I like to think about that is we usually plug in the x value to find the y value, right? And a common way I remember is usually, sometimes we write, instead of y, we have like f of x equals negative 4x plus 7. Like, we plug in an x, right? The x is what we control. We plug in what we want for x, and it spits out a y value. So usually x is our independent variable, but when we have parametric equations, X and Y are dependent upon T, right? So T is the independent variable. And so in this equation, X is the independent variable, but in parametric equations, T is. And since it says write parametric equations, we can write any set of parametric equations that make sense. So we kind of get to choose, and there's a dirty little trick, right? If X is the independent variable, but in parametric equations, T is the independent variable, we can just say X is equal to T. Why not, right? I get to make the parametric equations. It makes sense that if X is an independent variable in this equation, and T is the independent variable in parametric equations, then I can set them equal to each other, right? And so then from there, all we have to do is we do y equals -4, but now not times x, because x is t, right? And I guess usually when we write parametric equations, so that's one way. If we did x equals t again, usually for whatever reason, this time we sometimes like to write the t last, which seems a little weird, but either way works. And that's literally it, right? We've just called xt, and then in y equals -4, x equals 7, we've replaced t with x. And, again, on the surface, this is like, holy crap, that's easy, right? And it's just a matter of remembering when to do it. But the idea is we're introducing a variable time that we can need in a problem of some sort, right? So that's really it for that one. And you'll notice if we were to make, I'm not going to do it, but if we made a table of values like we did in number 2 yesterday, that table of values would also come out to be the same line as y equals -4, x plus 7, which is the whole point. All right, and then we'll do this example, and then we'll save the last one for tomorrow. The National Championship Air Race is held every year in Reno, Nevada. In the competition, supposed pilot Bob Hanna passes the starting gate at a speed of 410.7 miles per hour. 15 seconds later, Dennis Sanders flies by at 412.9 miles per hour. I don't know if those are real people. Those are the names the book gave me. They are racing for the next 500 miles. How long is it until the second plane overtakes the first? You could do this with lines, but the book wants us to work with parametric equations, so we're going to do so. Now, anyone in physics should know this, and I think most of us do know this in general. The distance something travels is its speed times the time traveled, right? If you're going 20 miles an hour, and you travel for an hour, 20 times 1, you should go 20 miles, right? So, and instead of like d for distance, I'm going to just call it x, right? If we go in the x direction, x is going to equal speed or velocity times the time, right? So we have Bob Hanna passes the starting gate at 410.7 miles per hour. So we could say their parametric equation is their velocity, which is 410.7 miles per hour times t, time in hours, right? The t should match the miles per hour. And then we can get x equals, and now we have to do the other one. Now, this guy flies by at 412.9 miles per hour, but 15 seconds later, right? So, this guy's time when he if he like makes this turn or whatever he does and he starts going, right, the other person already has 15 seconds ahead of him, right? So he actually almost needs like he needs a -15 here, right? Because we're counting the distance after that they've made this like starting gate pass, right? Or after they've passed the starting gate. And he doesn't do it for another 15 seconds. So that's why we have this t minus 15. But there's something that we need to be careful of 15 is in seconds, but 412.9 is in miles per hour. So we should make this 15 in hours as well. So to do that, you would do 15, right? And if you were to do, it's called dimensional analysis, right? If you do 15 seconds, I'm sure you guys can convert to hours, but you can do the dimensional analysis that 1 minute, 60 seconds, and then 1 hour, 60 minutes, right? So the seconds cancel with the seconds, the minutes cancel with the minutes, and then you're left in terms of hours. And what we end up getting is not t minus 15, but t minus, and my calculator is out of battery, so I'm just going to trust the book, 0.0042, just from dividing 15 by 60 twice, or timesing it by 1 over 3,600, right? And so this one's bad because we didn't want the minus 15. Right. And the reason we have to do this subtraction of the time here is because we're counting these equations together, right? It's a system together. Time 1 for this first person, right? If we counted that time for this person as well, that wouldn't make sense because they haven't passed the starting gate yet and haven't started moving, right? So we need to take into account and subtract the time difference. So from there, all we have to do is solve for t in each. Since we have x equals and x equals, we can set them equal to each other for 10.7 t, right? If x equals this and x also equals this, then they should equal each other. Oops. And then we just solve for t. 1.73418 is what the book is getting. I mean, from here, you guys know how to solve for this stuff. So we get about 2.2 t equals 1.73418, and then t would equal about 0.788. And that would be in hours, right? Which, if you did the calculation, would roughly come back to 47 minutes. And that tells us how long the second plane overtakes the first, because when they're at the same distance is when it's overtaken, right? So you have one that was already in the lead, or that got that 15-second head start, and you have the other one that passes the gate that's going faster. Eventually, it's going to catch up. So how long until it overtakes the first should be right when it catches up, right? And then they'll be tied, and then it'll take over. So right at around 47 minutes or 0.788 hours is when it'll catch up to the second one. And then how far have both planes traveled when the second plane overtakes the first? It's a good thing that we now have our time, right? And we have both of these equations, and they should yield the same distance, right? How far both planes traveled when the second plane overtakes the first. They should be neck and neck when the second one is starting to overtake the first. So we really only need to plug it in for one, and it should give us the same answer. So I'm going to do it to the easier one for 10.7 times t. 0.7 times t, which we said was 0.788. And that's just going to get us 323.6316. So 323 point, I'll round to the nearest tenth, 0.6 miles. All right, so that's the distance when they overtake each other, and there's the time. So this parametric equation was a little different because we don't have like x's and y's, right? But it's still just a parametric equation because we're involving t, which is time, and we're comparing two different equations. That is all I have for the example today. I know